All right, can you see my screen?
Yes, sir.
No, sir.
Not yet, sir.
No,
Not
sir.
yet.
Yeah, right now, can you see?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
All right, so let's start our journey over here. So I'm going to talk about today basically the vector and scalar. It's a very easy topics, right? Because all of you familiar with these topics, vector and scalar, but it still is very important. It's a very important topic. So the vector, we define the quantity which has the magnitude and the direction, right? And the quantity which has basically the magnitude that we define the scalar. Say, for example, if I say a car is traveling with 5 meters per second. So if I say it's a 5 meters per second, then it would be a scalar quantity, right? Which it would be basically the speed. But if I say the car is traveling 5 meters per second towards the north, then it would be that vector, right?
Yes, sir.
Because when I'm saying the car is moving at 5 meters per second, I didn't say which direction it moving. So that's why it has only the magnitude 5 meters per second. That would be basically the speed. This speed is a scalar quantity. It has no direction. But if I say the car is traveling in 5 meters per second towards the north, then it would be a vector. Then we can say it's a basically would be the velocity of that car. This velocity is a vector. We define that vector graphically. We can express that vector actually in the two way. One is the mathematical notation, which is actually in terms of your unit vector, and the second one the second procedure you can say we express by that graphically. So I'll talk about the graphically today. Then I'll talk about the mathematical explanation in the next class. So graphically we express a vector like that. Say if you have a vector A, we use that notation A, overhead arrow above the letter, right? And this is a symbol. And if you express in graphically, we'll use a length and a arrow. This length will give you basically the magnitude of that vector. This length will give you basically that magnitude, or will indicate the magnitude, and this arrow will give you the direction of that vector. By the way, my handwriting is too bad actually. So sometime I also intentionally do that in my in-person class, because you guys never ask the question in the class actually. So when you are trying to copy that lecture from the board, if you cannot understand my word, at least you will ask me that question, sir, what do you have written in the board? So that's why sometimes I do that intentionally. But that thing is not going to work in this live session. I know that one, because I'm taking it's recording. You don't have to copy from this one. But I'm trying to improve my handwriting. All right, so that's how actually we can represent the vector in the graphically. There are different type of vector we'll talk about over here. So first one I could say positive and that negative vector. What is that? Say positive vector will be that vector in any direction which you are considering the positive direction. Say a vector, this is the vector A, and towards the right, you are saying that your positive direction. That vector will be positive. If any vector towards in the opposite direction, that vector will be negative, right? It's like that actually. You are familiar with your Cartesian coordinate system. Say this is your Cartesian coordinate system. This is x-axis, this is y-axis, and this is z-axis. So any vector towards that direction, I will say is a positive vector because towards that is the positive x direction, and any vector towards in that direction, which is the negative x axis, I'll say that vector would be negative. That's how we can actually that indicate the positive and the negative vector. Second one we can categorize, which is parallel and anti-parallel vector. So if any vector in the same direction, say these two vectors are in the same direction, whether they are positive or they are negative, then these two vectors would be parallel vector. There is a mathematical condition over here. The angle between these two vectors would be 0. So that means we can say if the angle between the two vectors are 0, these two vectors would be parallel vector. Sometimes it could be they are equal magnitude, sometimes they could be different magnitude. Like now over here, A are B with that different magnitude because length of these are different over here. The anti-parallel vector, in that case, one vector would be towards that positive direction, and second vector would be towards in that opposite direction. In that case, the angle between these two vectors is basically 180 degree, right? So,
Yes, sir.
so that means if the angle between the two vectors are 0 degree, that vector are said to be parallel vector. If the angle are 180 degree, they will be anti-parallel vector. There is one more vector we categorize that called zero or null vector, which is basically has a zero length. I would say the zero length. So say if you have a vector A towards that direction, and you have another vector, the vector B, with the same magnitude. Look at this. I try to draw with the same length of this one. Well, it would be better for you if I write down in mathematical notation. Say the vector A is 5 I hat. Say I choose, so this is my Cartesian x-axis, and say this is my y-axis. This is a two-dimensional case, think about. In that case, the B would be, vector B would be minus 5 I hat, right? I hat is basically the unit vector in the direction of x-axis, positive x-axis. I'll talk about this thing, what is unit vector. Then, if you add this one or these two, A plus B, that's going to be the 5i minus 5i. That is going to give you basically that 0. That's called actually that null vector. So that's mean if you want to create a null vector, you have two anti-parallel vector with the same magnitude. If you add them together, you will find out a null vector which has a 0 length. Suppose I have a vector A, which I draw in that way. Now I want to draw the twice A vector. What I have to do, I have to just double it, right? So because I multiply with a scalar quantity with that vector A. So that's mean I'll draw, say this was the vector A. So I have to make it double. So that would be basically that twice A. So that's mean I can increase the length of a vector by multiply a scalar quantity over here. I can also flip the direction. So if I write, say that minus twice a, which would be totally in the opposite direction, right? So that means I'm just multiplying a vector by the scalar quantity. I can change the orientation of this vector in that way. That's called actually the multiplication. We'll talk about this thing in the multiplication. But let's think about one case actually. Say you have a table. It's a top view of the table. In the table, there is a point. Say the point is O, and the other point, say this is the point P. You want to go from point, say that from point O to P. So once you start from that point O, at the same time, say the table is moving towards that rightward with a constant velocity. If this happens simultaneously, so then after reaching the point P, you will find out that you are in a different point. Say that point is, say that S. Do you understand? Did you get my point? Say,
স্যার আমার কোশ্চেন ছিল এখানে।
sure.
এখানে হচ্ছে মানে আমরা যদি টেবিলটাকেও সরাই এবং সাথে যদি কেউ ও পয়েন্ট থেকে পি পয়েন্টে যায়, এরকম ব্যাপারটা?
Exactly.
আচ্ছা আচ্ছা। হ্যাঁ স্যার, তাহলে তো আমরা মানে ইসের সাথে ফ্লোরের সাথে সাপেক্ষে তুলনা করলাম, তাই না?
Yeah, so definitely.
আচ্ছা, হ্যাঁ স্যার, এটুকুই জানা ছিল।
Definitely. So I'm saying from out of this table, although you are claiming that you are standing at the point P, you're right, definitely. But I'm saying that you are not at the point P, you are point at the point SS. Both we are right. It's called the relativity actually. So that's mean your total displacement, I can say you start from that point, which is this one. This is one, and I can say your resultant displacement would be this from OS, right? It means I can write that OS would be basically OP plus PS. Can I write this one? It's a very fundamental law, very fundamental and very important law. The only law I'm giving you over here. So in the whole course, uh, I'm not going to recommend you anything to memorize, so or anything to carry in your head. But there will be 4 or 5 things I will recommend you. Try to keep this information in your head somehow. This one is among of them. This is known as actually the vector triangle law. So that's mean it's called that vector triangle law, which is a very useful law. So it means that you have a vector A, another vector is B, is connected in that way. Then your resultant would be this one, which is C. We can write A plus B must be equal to the C. It's known as the vector triangle law. It's a very important law. Very important law. And there is some condition to use this law actually. There's first condition. The first condition, the vector must be oriented in such a way the head of the first vector is connected to the tail of the second vector. Look at this over here. This is the case. The head of the first vector, which is the vector A, is connected to the tail of the second vector. It's known as actually head to tail connection. It must be arranged in that way. Head to tail connection. This is the first condition. Second condition, if the vectors are oriented in counterclockwise, look at this. If I move from A to B, I am basically moving in the counterclockwise direction, right? Then the resultant vector would be clockwise direction. This is the two condition to apply this vector triangle law. And this is the idea of adding to vector basically. Say in that way, say I'm going to write, say another case, say somehow vector A is over here and the vector B is over here. Now if I want to know what is A plus B, how I'm going to do that one? If it's mathematical representation, then it is very easy, right? Without knowing anything, you are just going to add them together. But that's not give you that actually the idea of what you are doing. Graphical representation is a very powerful. Once you understand the graphical representation, then without doing the calculation, you can predict or you can predict the trajectory of the particle, which direction it will move. That's very important for the mechanics. So that's why we are doing this graphical representation. Vector is very important. Very, you can never neglect that one. Say, for example, if I ask you why you are at the CSC department, what would be your answer? If I ask you why you are at the CSC department, what would be your answer?
So to learn about computer.
To learn about computer. That's great. Is there any more else?
To learn about the basics of physics and maths.
Then you should come to my department, MS department, not in the CSC department. Yeah, I know that CSC is also the application of the math, right?
Yes, sir.
Yeah, so general answer, most of the guys actually going to say, and that's true actually, you are going to be a engineer. Am I right?
Yes,
Yes,
sir.
sir.
At the end of the 4 year, you are going to be a skillful engineer, right? That's why you are at the CSC department at the Bragg University, and that's your target. That is actually the vector. You have some direction. You are going to be a skillful engineer. That is the direction of your life right now, right? That's a vector actually. Never neglect that. Vector is very important. If you are definitely in every step of our life, vector is a very important. We cannot neglect these things. So that's why we are still learning this thing at the very beginning of your university life, the first semester of your university life. Generally, that course should be in the first semester because you know this thing from the starting of your standard 6 or 7. So that's been from your school life, but still we are talking about this thing is the vector. It's a very important thing. So that's why the graphical representation is also very important. Graphical representation actually give you the idea without doing the calculation. You can visualize the direction of the particle, the trajectory of the particle, which is very interesting. So that's when without doing the calculation like magic, you can say that the particle is moving towards in that direction. It will look like a magic. If you can develop this thing inside yourself, then definitely you can say that one. All right. So now for this case, if I want to find out the A plus B graphically, will it be possible? Because I have only one rule, which is actually that vector triangle rule. Still, I know this thing, right? Nothing more than that. But it's not going to be that in that way because it basically the violating the first condition. It must be the connected to head to tail connection. The vector are not oriented in such a way over here. So then what can I do? I can do one thing, say I can shift that origin of that vector from here to here. I can do that without changing the direction and the magnitude. you can change the origin of that vector anywhere you want. Because if you do that, you are not changing the vector at all. Because you are not changing the direction, you are not changing the length of the vector. It means that vector is not changing. If you just shift the origin, the vector is not going to be the change. So that's why you have that power. You can shift the origin from anywhere you want. If I do in that way, now it satisfies the first condition of the vector triangle law, which is head to tail connection. Now I can draw that resultant vector from tail of the first vector to the head of the second vector. Basically, that would be that my a plus b, the addition of these two vector. Right, so that's actually the vector triangle law. What if I can also do in another way? Say this is my vector A, and say this is the vector B. Right, if I want to again find out, say that A plus B, what I have to do? I have to do basically, I have to rearrange that vector over here because they are not again head to tail connection. What I can do, I can shift that origin from that vector from here to here. Oh God. Working, I'm sorry. All right, so you can do actually that. So you can shift that vector that way, and you can also take it over here. So if you do that, so this would be actually again head to tail connection. I can say this would be actually that B plus A. And remember, this B plus A would be equal to the same, that A plus B. It's known as actually the commutative law. Which is actually the extended version of that vector triangle law. It's called actually that commutative law. It's the same thing actually over here, because I can rearrange that one. Look at this. I have that vector. Is the vector A is over there, and vector B is over there. Right? That was the orientation. So what I did over here, I just shift that part. Instead of doing this thing, if I say I'm going to do, I'm just going to shift that case actually. It's not working, I'm sorry. If I shift that A over there, which is this one, then I will find this case, right, which is actually B plus A. Now, instead of doing that, if I say that I'm shifting the B, say I draw over here for you, say this is the new location of that B, then A plus B also going to be indicating the same vector over here, because head to tail connection. So that's why B plus A must be equal to A plus B, which is known actually that vector commutative law, which is actually the extended version of the vector triangle law. All right, say, what about, say, if I want to find out that A minus B, say the vector is oriented in such a way, so this is the vector A, and say this is the vector B. I want to find out that A minus B, or the subtraction of these two vectors. What would be that? What do you think? So, should we introduce one more law to find out this subtraction of the two vector?
Sure, sir.
Right. Say when you give some instruction to your machine in your computer, say that 5 plus 7, it automatically give you the 12, right? But when you give the instruction 5 minus 7, it automatically give you the minus 2. Do you think that the computer performing these two operation using two different coding or different program? Hmm?
Yes, sir.
Is it?
Yes, sir.
In that case, your operating system should be more than 20 GB. So that's mean for every operation you have to write down the code. And what is the purpose of using this machine? It's not. It's basically using the same operation in that way. 5 plus minus 7 is actually adding. It's actually using the same program to perform the two operation. That's why human being actually created this machine. Right? So it's give you basically that minus 2. It's using the same program to perform this operation. But before doing this operation, it's flip that number actually. So in that way, we can do that one. Say if we shift that B over here, just multiplying by a scalar quantity minus 1, this will basically that change the direction of the B. It will flip the direction of the B. After flipping the direction, I can shift that origin of that minus B vector from here to here, right? Now they are in satisfying the first condition, it's a head to tail connection. Then I can say my resultant vector will be this one. Sorry, this will be my resultant vector, which is, although you are adding in that way, say that you will write A plus minus B, which is actually A minus B, which is indicating that vector. That's how actually we can add or subtract of two vector graphically using this vector triangle law. And it's a very important law. In every, starting from here, I will, in every case, I'll try to utilize this law actually to build up that how to take the component of a vector, how to segregate the component of a vector in different axes from different coordinate system. So that's why even in the Newtonian mechanics of that part of the Newton's law of motion, or motion in a 1D and the 2D, I will use that idea. I will try to utilize this idea. Whenever I get the scope, I will try to use this vector triangle law. And that's why it's a very important law. Very fundamental law and very useful law. It's a two-handy. That's the case actually. In that way, we are going to use this vector triangle law. There is one more case actually. Say if you have more than two vector in such a way, so this is the vector array, and they are in different location, and I have arranged them in that way. Head to tail connection. I just shift that origin without changing the magnitude and the direction of those vector. I just shift that origin. Then how I'm going to find out that addition of this vector A plus B plus C? I know it's very easy in mathematical notation, but graphically, what you can do, since we have only one theorem, which is the vector triangle law, in that case, we can use only the two vector. I'll do that step by step. First, I will add, say that A plus B, it will give me that one, right? So this is will be my A plus B. In that case, I can neglect this one. Right now, this A plus B head is connected to the tail of that C vector. Then I can say the resultant vector will be this one, which is actually that A plus B plus C. Again, I'm using that vector triangle law. Or you can do it in another way. Say you will first say I'm going to first add B plus C, this one. I should use different color. So I'm going to add first B plus C. They are head to tail connections. So this is actually B plus C. And this B plus C vector is connected with the head of the vector A, head to tail connection again will be. Then again, this will be your resultant vector. So that's mean if you write in that way, A plus B plus C must be equal to A plus B plus C, which is known actually the vector associative law. That is also an extended version of the vector triangle law. That's how actually we can apply this law in our case when we're going to deal with this matter. When we get this scope, we'll try to apply this law. All right, that's all for today. Do you have any question up to that? Whatever I said?
No, sir.
No, sir.
Sir, can we get the YouTube channel link of your?
Yeah, definitely. I'll give you that link. Do you need right now?
Yes, sir.
Or right now I have
So
some.
you can give it in the Slack.
Yeah, I'll give you into the Slack. In my Slack channel, I'll give you that link. All right, thank you very much. If you don't have any question, you can leave, you guys. See you in the next
Okay.
Tuesday. So next Wednesday.
Okay. Thank you, sir.
আসসালামু আলাইকুম স্যার, আল্লাহ হাফেজ।
Assalamu alaikum.
Assalamualaikum, sir.
Assalam.